Hello, Math 6B people. All right, today I got a video for you entitled Things You Can Do with a Fourier Series. Now, I should point out, this is definitely not all the things you can do with a Fourier Series. There's lots more, including the stuff that'll be towards the end of the class, which is you can use a Fourier Series to help you solve a partial differential equation. Okay, so, and I'm going to use an example that I already derived the Fourier series for. So we had this function here, f of x was x squared on the interval minus pi to pi, and it had a period of 2 pi. Remember, this was the 5-year-old draws the ocean function. And we figured out that this crazy thing down here was the Fourier series for it. And so what I want to know is now, well, armed with this Fourier series and the fact that we know that this Fourier series down here is the same thing as this function up here, then what do we do with it, right? Like, we don't just find the Fourier series to find the Fourier series. We then do things with the Fourier series. So so let's see here. Well, a couple of things that we can do once we have this series is we can plug in an x value in order to evaluate an infinite sum. And it's not always immediately clear, like, starting from a function, what sorts of infinite sums you'll be able to evaluate with it. But you get a whole bunch of them for free because you know that this function is the same thing as this sum, no matter what I plug in for x. So, well, provided it's not at a point of discontinuity and blah, blah, blah. All right, so let's see here. So let's evaluate some sums. All right, so I'm going to write the Fourier series here. And so this was pi squared over 3 plus the sum as n goes from 1 to infinity of, what was that, an? The an was 4 times negative 1 to the n over n squared. So 4 times negative 1 to the n over n squared, and then that times cosine nx. And then this was equal to x squared if x is between negative pi and pi, and it's equal to f of x plus 2 pi otherwise. Okay, so as long as I'm plugging in x values between negative pi and pi, then I can just set it equal to x squared. So, all right, well, okay, so let's see. Let's just plug in some x values and see what happens. So for instance, if I plug in x equals 0, then we can evaluate this sum. The sum as n goes from 1 to infinity of negative 1 to the n over n squared. Okay, so how does this work? Well, let's see here. If I plug in x equals 0, that's in the interval minus pi to pi. The whole thing's equal to 0. So f of 0 is just 0. So note f of 0 is just 0. So we get that if I plug in x equals 0, and the cosine of 0 is just 1, by the way, then we get pi squared over 3 is the same thing, or plus the sum as n goes from 1 to infinity of 4 times negative 1 to the n over n squared times the cosine of 0. That is supposed to be equal to 0, right? Because when I plug in x equals 0, the function's equal to 0. And if the sum is in fact the same thing as the function, well, then, yeah, this should be true. Okay, so since the cosine of 0 is 1, we can pull out the 4 out of the sum, and we get pi squared over 3 plus 4 times the sum as n goes from 1 to infinity of negative 1 to the n over n squared. That's 0. And we could just like subtract the pi squared over 3 over to the other side and then divide by 4. And then we get the sum as n goes from 1 to infinity of negative 1 to the n divided by n squared is equal to minus pi squared over 12. You might be wondering what's the deal with the minus. Well, if you notice, the n equals 1 term here gives you a negative. So the leading term of this series is negative, and the rest of them get smaller. So yeah, it's going to give you a negative number. If you want to make it look prettier, because it looks prettier if you get a positive number for the sum, we can just multiply both sides by -1. So if we multiply both sides by -1, then this becomes n goes from 1 to infinity of -1 to the n plus 1, right? We just multiplied it by another -1, and then that adds up to positive pi squared over 12. Interesting. And so, yeah, or if we write out the first few sums, it's like if I do 1 minus a ninth, no, 1 minus a fourth, right? 1 minus 1/4 plus 1/9 minus a 16th plus 1 over 25, etc., etc., etc. That apparently adds up to pi squared over 12. This is a particular sum, and the next one we do that we would not have been able to do using, we would not have been able to figure out what this sum added up to using like Taylor series methods. All right. So what about, let's try another one. Well, another like kind of easy one to plug in would be x equals pi into here. So what's f of pi? Well, again, pi's in this interval, negative pi to pi. It's right on the edge of the interval. So I get pi squared if I plug in. So if I plug in, as it happens, if I plug in x equals pi into this series, as we'll see, we can evaluate this sum. N goes from 1 to infinity of 1 over n squared. And now again, this is one of those ones that you would not be able to figure out using like Taylor series methods. So let's see. Well, again, f of pi. You know, if I look at my original function, if I plug in x equals pi, I get pi squared. Okay, so that means that if I plug in x equals pi into the Fourier series, this doodad, then well, the whole thing should be equal to pi squared. Okay, cool. So let's do that. So that means pi squared over 3 plus the sum as n goes from 1 to infinity of -1 to the n, 4 times -1 to the n over n squared times cosine of n pi, right? So this is just, we replaced the x with pi, okay? And that's supposed to add up to pi squared. And again, if we do a little bit of rearranging here, one thing to note is that, remember, cosine of n pi, that's the same thing as -1 to the n. And -1 to the n times another -1 to the n, that would just be 1. Cool. So this cleans up quite a bit. So we get pi squared over 3 plus, I'll pull the 4 out. N goes from 1 to infinity of just 1 over n squared. That adds up to pi squared. All right, subtract the pi squared over 3 over to the other side. 4 times the sum as n goes from 1 to infinity of 1 over n squared equals, so if I have a square pi and I subtract 1/3 of a square pi, then I have 2/3 of a square pi, so 2 pi squared over 3. And then I divide by 4, and all of a sudden, I get the value of this sum, 2 pi squared over 12, so I guess that's pi squared over 6. Interesting. All right. So now, again, we were able to evaluate this sum by just having pre-computed the Fourier series for a particular function. Okay. So, all right. Now, if we plug in other x values, we can get other sums. I will leave that to you to figure that out. And in fact, if I figure out the Fourier series for a different function, then I could plug in some x values into that and figure out even more sums. And so we could just keep this growing list of like sums that I know what they add up to from this. Okay, now here's a second completely different thing that we can do with Fourier series, and this is a sketch of graph of the coefficients versus frequency. And what you'll get is apparently This is a very mysterious thing. If you read this before you watched the video and said like, "What do you mean? What does f of x sound like?" It's probably hugely confusing. Um, but I promise it will make sense after I explain it. So 2. Let's see here. What does f of x sound like? All right. So what do I mean by this? Well, let's see here. Let's take a look at a graph of f of x and imagine like x was time and f of x is sort of like amplitude, right? So we got x, f of x. And remember, our function was like this parabola from minus pi to pi. And this had a height of pi squared there, right? And then this parabola repeats itself, right? So like, and so I want to know if this was a sound wave, what would it sound like? Well, now let's think a moment about sound waves or whatever. We tend to think of sound waves in terms of volume and pitch. So volume is sort of like amplitude. It's really more like amplitude squared, but all right, well, for the moment, we'll pretend it's just amplitude. And then pitch is more like frequency. Oh, okay. So if I know how loud, so if this was a sound wave where this was like air pressure versus time, then if I know how loud it is at each frequency, then that would be a better description of like what it sounds like than like merely the graph of a sound wave as a function of time. So now if we look at the first few terms of our Fourier series. All right, so the first few terms of our Fourier series were, so our f of x was, so we had the constant term, pi squared over 3. So this, by the way, this would be like the 0 frequency. And then, so the next term would be minus 4 over 1 squared. So minus 4 over 1 squared times cosine 1x. And then plus 4 over 2 squared cosine 2x. And then minus 4 over 3 squared cosine 3x. And then plus 4 over 4 squared cosine 4x, et cetera, et cetera, et cetera. All right, and we could keep going, right, as far as we please. But the idea is that we think of our quote unquote sound wave as a whole bunch of different sine waves, pure tones added up, right? We've got an amplitude, well, ignore the minus sign, we'll just do the absolute value of the coefficients. So we've basically got at a frequency of 1, so this is like, well, it's angular frequency, I suppose, omega equals 1. We've got an amplitude of 4. And then at a frequency of 2, we've got an amplitude of like 1, I guess, right? And then at a frequency of 3, we have an amplitude of 4 over 9. So it's like basically as the frequencies get higher, we get pure tones at integer frequencies, and you know, you could scale it so that you can make the base frequency whatever you want, or the fundamental frequency, I guess. And they get quieter as you get higher in pitch. And so we get a graph here of, so if I sketch the absolute value of AN versus frequency, and I'll get a little stem plot. All right, so it's omega and absolute value of AN, right? So at 0 frequency, we get like pi squared over 3, which is, that's a little more than 3. So it's like, so this is like at 0 frequency, this is at pi squared over 3. This will be a rough plot, a little more than 3. And then at a frequency of 1, we get an amplitude of like 4, which would be a little bit higher than that. And then at an amplitude, at a frequency of 2, we would get an amplitude of like 1. So this is a height of 1. So I'm just labeling the heights here. And then at a frequency of 3, we would get an amplitude of 4/9. So that's a little less than a half. So it's like 4/9. And then at a frequency of 4, we would get, what is that? 4/16. So that's like 1/4. So that's even smaller. Right, and then at a frequency of 5, we get something even smaller than that. At a frequency of 6, we get something even smaller than that. At a frequency of 7, we get something even smaller than that, and so on and so on and so on. Okay, and this, if we were treating it as a sound wave, this is a much better description of what the wave sounds like than the original graph, right? It tells you, well, it's loud at that frequency of 1. Cool. And in fact, you may have seen a graph like this before in a non-academic context, namely, the low frequencies are usually labeled bass. The ones in the middle are usually labeled mid. Seems like a reasonable name for the frequencies in the middle. And then the high frequencies are usually labeled treble. And so what we have is like what the sound wave would appear like on a graphic equalizer, like for your stereo or whatever. Oh, so it turns out that whenever you're looking at the equalizer for like, say like music that you're listening to, like on your music player, if you're looking at the equalizer, what you're really looking at is the Fourier coefficients of what you're listening to. So all of your music players know how to compute Fourier series. So the lesson is if you want to be smarter than your music player, then you should learn to do Fourier series. Hopefully that's some motivation. All right. Have a good 3-day weekend, everybody. I will see you next time.